Professor David Hand, who shared the international jury, will now introduce the laureates. David Hand is Professor Emeritus of Imperial College in London. He has written many books, some of which popularize statistical topics for a broad audience. He was appointed officer of the Order of the British Empire and elected Fellow of the British Academy. Please, David.
Thank you very much. I was honoured to be asked to chair the selection committee again. And again, I'd like to say how grateful the statistical community is to Peter Russo for establishing this prize, and to thank the administrators who promote, advertise and solicit nominations, and my fellow selection committee members for our discussions on who should be awarded this year's prize. The Nobel Prize was established in 1895 for the disciplines of physics, chemistry, physiology or medicine, literature and peace. A sixth prize for economics was established in 1969. The Turing Prize for computer science was established in 1966, and the Abel Prize for maths was established in 2001. But the gaping lacuna in that list is difficult to miss. Statistics, that I define as the discipline of extracting understanding and illumination from data, is central to modern civilization. It's ubiquitous, impacting all walks of life, from medicine to finance to public policy and government, even though one may have to look under the hood to see it. I might go so far as to say that none of the disciplines included in the Nobel Awards would be possible in their modern form without statistics, perhaps with the exception of literature, although perhaps somebody can point out to me a recent Nobel Prize-winning book that depended on statistics. So it was a gap that was crying out to be filled, and the Russo Prize does just that. Now, my role here today is first to spend a few minutes describing the winning work in a high-level, informal and non-technical way, and then to introduce the prize winners. I apologise if this repeats, I might say, replicates some of the material that you've heard earlier for those who are here before the musical interlude. I'm going to begin by looking at a couple of examples. Your blood pressure fluctuates from day to day, over time of day, and even depending upon whether you've been sitting or walking just before it was measured. It's affected by a multitude of random influences. So if I were to measure the blood pressure of everyone in this room, some of you would have a high value, perhaps even above the threshold, which would prompt concern. But only for some of those would it be because you really had an underlying condition that might merit treatment, while for others it would be high simply because one of those other random influences had temporarily made it high. In this context, a false positive or false discovery is a test result which indicates something abnormal when really there is nothing abnormal. If I rushed everyone who had a high blood pressure reading off to the hospital, many of those would turn out to be perfectly normal on closer investigation. This would be bad news for all of those who'd been rushed off, not merely because of the time wasted, but also because of the anxiety caused. Indeed, some medical screening programs have been criticised for these very reasons. Being told you might have cancer and then suffering intrusive investigations and perhaps even surgical operations, only to later discover that it was a false positive, is clearly to be avoided. So how can we reduce the number of such false positives? One way would be to use a higher threshold, which must be exceeded if we're to classify blood pressure as concerning. Indeed, by choosing a high enough blood pressure threshold, I can make the number who've been unnecessarily rushed off to the hospital as small as I like. But there are a lot of people with normal blood pressure in this room. Even if I chose a threshold sufficiently high that any one person has a very small chance of being incorrectly flagged, with so many people, the chance that I incorrectly flag one or more is large. To make my chance of incorrectly sending anyone to the hospital, I need to set the threshold so high that most of those who do have hypertension will be missed. This rather defeats the object of the exercise. We seem to have something of an impasse. It is at this point that today's laureates came galloping to the rescue. They developed a very clever, novel strategy for tackling this problem, which I'm going to describe in a moment. But first, let me give my second example. In image processing, a pixel is one of the tiny dots that make up the picture. If you look at an image or a computer screen in high magnification, you can see the dots, but from a distance they all merge together to give a continuous picture. Medical scanning involves X-rays or other methods to take images of slices through the body, and then it puts all those slices together to give a three-dimensional image of the inside of your body. So that three-dimensional image is made up of lots of tiny three-dimensional dots. They're called voxels. What we'd like to know is if any of those voxels, or regions of voxels, appear abnormal. Are they too bright? Again, we can test each of those voxels, but random variation means we should expect that sometimes perfectly normal regions of the scan will show up brightly. And if we test lots of them, we're pretty well guaranteed that some regions of the scans of perfectly healthy people will show up brightly just by chance. It's just like my blood pressure example. A paper published in 2010, and which has now become a minor classic, illustrated the problem perfectly. The paper says, and I'm quoting, one mature Atlantic salmon, a fish, participated in the fMRI study. The salmon measured approximately 18 inches long, weighed 3.8 pounds, and was not alive at the time of scanning. It was dead. Image acquisition was completed on a 3.5 Tesla G Signa MR scanner. A quadrature birdcage head coil was used for RF transmission and reception. And a paper goes on like that for several paragraphs, giving details of the experimental setup. Before continuing, the task administered to the salmon involved completing an open-ended mentalizing task. The salmon was shown a series of photographs depicting human individuals in social situations. The salmon was asked to determine which emotion the individual in the photo must have been experiencing. Now, at this point, you're probably thinking to yourself that it's pretty clear what response the dead fish will give to being presented with the photographs. But here comes the crunch. The paper says voxel-wise statistics on the salmon data were calculated. Now, you'll remember from my description of what a voxel is that there will be a large number of them in any particular three-dimensional image. In the salmon's case, there were 130,000. This is like the blood pressure example, but instead of 100 or so tests, the number of people in this room, there's a vast number of tests being conducted. Carrying out separate tests on such a large number of voxels will almost certainly result in some showing apparent effects purely by chance because of the measurement error and so on. And that is indeed what the researchers found. They report several active voxels were observed in a cluster located within the salmon's brain cavity. They went on to say, either we have stumbled onto a rather amazing discovery in terms of post-mortem ichthyological cognition, they mean dead fish thinking, or there's something a bit off with regard to our uncorrected statistical approach. Could we conclude from this data that the dead salmon is engaged in the perspective-taking task? Certainly not. By controlling for the cognitive ability of the subject, we have thoroughly eliminated that possibility. They mean the fish was dead, so couldn't think. What we can conclude is that random noise may yield spurious results if multiple testing is not controlled for. Of course, the aim of the authors of that paper was to drive home the consequences of failing to take account of the number of tests being conducted. They also included more appropriate analyses, including those based on the work of today's laureates. So I've given you two examples. A third, which you've heard already today, occurs more generally in science. If scientists explore a great many different hypotheses, arranging so that each one has a chance of only 5%, say, of being supported incorrectly, it means that the chance of accepting at least one incorrectly is very large. And given enough such hypotheses, this could result in accepting a large number of hypotheses which aren't true. It will mean that scientific claims are made which are later found to be false. This has become a real problem in some scientific disciplines where it's known as the reproducibility crisis. So we've got a problem. Major breakthroughs in science come from looking at things from a different angle, followed by a lot of hard work and a struggle for acceptance. I'll come to the hard work and struggle for acceptance in a moment, but first let's look at the insight the laureates had, which led to the work which has been presented today. In my first example, I looked at the chance of incorrectly flagging someone with normal blood pressure as hypertensive, and the opposite chance of incorrectly labelling someone with abnormal blood pressure as normal. That's all very well. But now put yourself in the hospital's position. What you'd really like to know is, of all those I send to the hospital, what proportion of them really have high blood pressure? If it turns out that only 1% of them really have high blood pressure, the hospital would stop asking me to waste their time and resources. But if it turned out that 99% did, then they'd be very grateful. Let me make this more general. Suppose instead of people, I'm testing many different drugs, or many different scientific hypotheses, or many different financial trading systems, whatever. The traditional perspective tells us what proportion of the ineffective drugs I claim are effective. The new perspective tells us of those drugs I claim are effective, what proportion really are. That's often a much more relevant question. It's telling us how many of my claimed scientific discoveries are real. And its complement is telling us how many of my claimed discoveries are false. It's telling us the false discovery proportion. But you may have spotted a difficulty here. We can't tell how many of this claimed discoveries are false because we don't actually know which are true and which are false. That's the whole point. That's what we're trying to find out. It means we can't actually calculate the false discovery proportion, so we can't limit it, we can't control it. And in a seminal breakthrough paper published in 1995, which you've already heard about, Yoav Benjamini and Josef Hochberg cracked the problem. Again, it's all about perspective and looking at problems in the right way. Instead of looking at the observed false discovery proportion, they looked at what you'd expect it to be based on the data. They call this the false discovery rate. And then using some clever mathematics, which you've already seen presented to you, they showed it's possible to control the value of this. That is, we can ensure that the false discovery rate is less than any value we want. We can control it. However, it has to be said that few people initially recognized the importance of the work or how widespread its use would become. This is the struggle part. It's traditional in science that papers are sent out to other experts in the field to be reviewed and commented upon. Is the data sound? Are the methods fully described? Do the conclusions follow? And so on. The paper will then probably be sent back for revision, often several times, with no guarantee of acceptance. Often journal editors decide that the submission doesn't quite match their aims for the papers for the journal, and it will be rejected. So one submits the paper to another journal. This is all standard procedure, but it means that the process of getting a paper published is slow and painstaking. Yoav Benjamini says of the 1995 paper, 5 years and 3 journals later, the paper was accepted for publication. I imagine that the editors of those journals who rejected it felt a bit like all the publishers who rejected J.K. Rowling's first Harry Potter book and kicked themselves. Other papers on the false discovery rate concept suffered a similar protracted struggle before they were eventually published. Now, the discipline of statistics is constantly advancing. Peter Russo mentioned this earlier. New kinds of problems are arising. New types of data are being captured. New questions are being asked. And new methods have to be developed to cope with those changes. The development of the Benjamini and Hochberg method illustrates this perfectly. The method gradually gained traction as researchers recognized that it often answered a more pertinent question than the traditional approaches. But it was the advent of new kinds of data which really gave it a boost and catapulted that 1995 paper into being one of the most highly cited papers in statistics. In particular, genetic data that you've already seen described in the form of DNA microarrays arrived. This is characterized by thousands or tens of thousands or more of genes being tested simultaneously. It's a perfect illustration of the multiple testing challenges I've outlined in my early examples. And this new kind of data required a solution which had already been developed in the 95 paper. But of course, things don't stop there. The original paper, as you've heard, assumed statistical independence of the multiple test statistics. That's not always a realistic assumption. Yoav Benjamini and Daniel Yekutieli went on to relax this constraint, and together with Ruth Heller have subsequently gone on to extend its application in various other directions. So let me introduce the laureates. Daniel Yekutieli is an associate professor in the Department of Statistics and Operations Research at Tel Aviv University. He took a BSc in mathematics from the Hebrew University of Jerusalem in 1992, a master's in 96, and a PhD in applied statistics in 2002, supervised by Yoav Benjamini. Between 92 and 97, he worked in the research department of the Israel Meteorological Service. It was Daniel's father, a physicist, who suggested he consider statistics as a career, which is why he moved to Tel Aviv University. While he was there, he was encouraged by Josef Hochberg and started working with Yoav Benjamini. Daniel says of Hochberg, Yossi was a very generous and smart guy. He made me feel very welcome and even gave me consulting projects to do. And of Benjamini, he says, he seemed very kind, dependable, and always open to new ideas. All true. And I liked his outlook on statistics. Ruth Heller is a professor in the Department of Statistics and Operations Research at Tel Aviv University. She took a BSc in mathematics from McGill in 96, where she received some very wise guidance from Professor David Wolfson, who told her that biostatistics is the most beautiful profession. Quite right, of course. Professor Heller then went on to take an MSc in biostatistics from the University of Washington in Seattle in 98, and a PhD in statistics from Tel Aviv University in 2007, supervised by Yoav Benjamini. She spent extended periods at the National Cancer Institute, the University of Pennsylvania, and Technion, the Israel Institute of Technology. By this point, you will have spotted the common factor throughout all of this work. Yoav Benjamini is the Nathan and Lily Silver Professor of Applied Statistics at Tel Aviv University. He studied mathematics at the Hebrew University of Jerusalem, from which he graduated in 1973 and received his master's in 76. He then went to the United States to take a PhD at Princeton, graduating in 81. He spent time as a visiting professor at various universities, including the University of California, Stanford University, and the Wharton School in Pennsylvania. He's received many awards for his work, including the 2012 Israel Prize, the Medallion Lecture of the Institute of Mathematical Statistics, and being elected to the Israeli Academy of Sciences and Humanities and the United States National Academy of Sciences. Those are today's three laureates, but I also want to mention one other person whose name has cropped up repeatedly, both in my presentation and earlier today. This is Josef or Yossi Hochberg. Regrettably, Josef Hochberg passed away in 2013. Had he still been with us, he would certainly have been one of the laureates. His earlier work, such as his 1987 book, Multiple Comparison Procedures, underpinned what I've been describing and what has been described earlier today. And his continued work through the seminal 95 paper into the present century led to significant development of the ideas. The 1995 Benjamini and Hochberg paper is one of the most highly cited of all scientific papers. What that means is that a huge number of other researchers have used the method and developed it further. That 95 paper was the start of a revolution which has benefited all of humanity in countless ways. Thank you very much.